What if I told you that the simple act of flipping a coin, the reason your coffee gets cold, and the way your DNA stores the blueprint for life are all governed by the exact same deep physical principles? Well, they are. Welcome to the absolutely fascinating world of information physics.
It sounds like the setup to a really nerdy joke, right? But the answer isn't a punchline. It's a single, fundamental concept that completely redefines what we even mean by the word information. Today, we're going to pull on that thread and see how it connects, well, pretty much everything.
So, first things first, we have to get past our everyday idea of what information is. We need to look beyond just words on a page or computer code.
You know, when we talk about information, our minds jump to things like books or the ones and zeros that make up a computer file. But what physics tells us is that that's just the surface. We have to go deeper, to a level where information isn't really a thing at all. It's something else entirely.
And here it is. This is the absolute key. Information is a relationship, a connection. It doesn't actually exist in any one thing by itself, but in the correlation between two things. An example makes this crystal clear.
I love this example because it illustrates the point so perfectly. Think about it. The information in a star map isn't just the ink on the paper. That's meaningless by itself. The information only exists because that pattern of ink is correlated with the pattern of actual stars in the sky. If you burn the map, poof, the information is gone. But, and this is the cool part, if you could somehow magically rearrange all the stars, the map becomes useless, and the information is also gone. It's all about that correlation.
Okay, so if information is a correlation, how on earth do we measure it? Well, the answer, believe it or not, starts with something incredibly simple: flipping a few coins.
Just think about it for a sec. 2 coins. You could get heads heads, you could get heads tails, tails heads, or tails tails. That's it. 4 possible outcomes. This simple idea of just counting up the number of possible outcomes, or choices, is our first step to actually putting a number on information.
And just look at how fast the number of possibilities explodes. With 1 coin, you have 2 choices. Easy. Add a second coin, you've got 4 choices. Add a third, you're up to 8. By the time you get to just 10 little coins, you've got over 1,000 different ways they could land. This exponential growth is absolutely fundamental here.
And this finally brings us to the famous bit. A bit isn't just a 1 or a 0 in a computer. At its core, it's the fundamental unit we use to measure uncertainty, or, and I love this term, surprisal. The uncertainty of a single coin toss, where you don't know if it's heads or tails, that is exactly 1 bit. 2 coins? That's 2 bits of uncertainty, which leads to our 4 choices. It's just a beautiful, simple way to measure what we don't know.
And if you want to see this in the real world, just look at the screen you're watching this on right now. A standard 24-bit color display doesn't have 24 colors. Nope, it has 2 times the power of 24 possible color choices. That's almost 17 million different colors. Every single pixel holds 24 bits of uncertainty about which one of those millions of colors it could be.
So we have this cool way to count choices using bits. But what in the world does this have to do with physics, with heat, with energy? Well, hold on, because this is where everything clicks into place.
Okay, so we've nailed down this really elegant little rule. The number of possible choices is always 2, raised to the power of the number of bits. Just remember that relationship, because we're about to see it show up somewhere you would never, ever expect. Now look at this. This is one of the most important equations in all of physics. It's so important it was literally carved onto the tombstone of the great physicist Ludwig Boltzmann. It defines a concept called entropy. Now look closely. S is entropy, and that W? Well, W stands for the number of possible microscopic states a system can be in. In other words, W is just a fancy physics name for choices. It's the same idea.
And the implication here is just staggering. It means that thermodynamics, the physics of heat and energy, is fundamentally just a form of information theory. Entropy is just a measure of our uncertainty. It's the missing information about a system's microscopic state. Your hot cup of coffee cools down because its energy spreads out into a state with more possible arrangements, a state with higher uncertainty, or as we'd say now, a state with more bits.
So once you make this connection, this lens, you start seeing it absolutely everywhere. This one concept is like a master key that unlocks secrets in dozens of completely different fields.
Seriously, think about this. This single idea of measuring uncertainty in bits underpins thermodynamics, yeah, but it also explains how zip files compress your data. It's used in biology to map out genetic family trees from DNA sequences. It's even used in plagiarism software to figure out how much information one essay shares with another. And, get this, in law to actually quantify the strength of evidence in bits. It's the same core idea over and over and over again.
Okay, but wait a second. If information is tied to disorder and uncertainty, if things tend to spread out, then how does anything complex ever get built? How does something like life even happen? Well, information physics has a mind-bending answer for that too.
So first, we have to make a distinction between two types of complexity. On one hand, you've got analog complexity, like a crater left by a meteor. It's just a direct physical impression made on the world. But then you have digital complexity, and this is the game changer. Think of DNA. It's not just an impression, it's a stored, replicable code. It's a recipe that can be copied almost perfectly.
So what's the engine that drives the creation of all this amazing complexity? It's the flow of energy. Life doesn't violate the second law of thermodynamics. It cleverly exploits it. You can think of life and other complex systems as these little eddies, these little whirlpools in the great river of energy flowing through the universe. They build up these amazing pockets of localized order and information by taking in ordered energy, like sunlight, and spitting out disordered energy, like waste heat.
And what's truly incredible is how this process builds on itself in layers. First, you get the analog complexity of planets forming from stardust. Then, on some of those planets, digital complexity emerges with DNA, and boom, you have life. That life evolves into more and more complex forms, and eventually some of those forms develop their own digital information systems, like language and culture. Each new layer of correlation is built upon the last.
And that leaves us with this final powerful thought. Energy is always conserved. It can't be created or destroyed. But complexity, order, information, they are not. They are fragile. They are like ordered energy, so easily lost, and they can only be maintained with great care. It's a humbling reminder that from our very DNA to the whole of human culture, the information that defines us is a precious, delicate thing. The real question is, what does it mean for us to be the caretakers of all this complexity?